So today we're going to look at a branch of mathematics that's hugely important in the modern world because much of this branch of mathematics is done with computers, and it doesn't get a lot of credit. It's not one of the more famous pieces of mathematics, but it is enormously important. The branch of mathematics is called numerical methods. Now, the majority of the maths we do at A level and below, we use what are called analytical methods. When we try to solve a problem, we might use, for example, an algebraic process or an exact procedure. And if you apply that procedure or method, you get the exact or correct answer. Numerical methods apply to much harder problems, but they give us typically inexact solutions, but solutions which are sort of close enough for any practical purpose. So suppose I wanted to solve an equation like this. You know how to solve this equation. You can probably look at it and do it in your head. But suppose I was asking somebody at primary school that had never seen algebra before, and I said, "Oh, what's the value of x there?" A typical first approach might be to literally guess. You pick some numbers and see what happens. So you might say, "Oh, maybe x is 2. Well, 4 times 2 is 8. Add 9. No, that's only 17. That's not enough." And then you might think to yourself, well, because my guess gave me 17, which was too low, I probably ought to try a bigger number. So, oh, how about 4 times 4 is 16? I don't know, that's only 25. How about 4 times 5? I know. Oh, yes, it works when I do 5. So what I've done there is a numerical method. It was an example of trial and improvement or trial and error, but that was a numerical method to solve this. If you said take 9 from both sides and divide by 4, that's an analytical method. It's a process that would give you the answer. Suppose I have a graph over here. I might even know the equation of this graph, and I want to know what would the equation of a tangent be drawn at this point. Now, you know the analytical method here. The analytical method for figuring out what the equation of the tangent here is to differentiate the equation of this curve, put the x-coordinate in here, and you're going to get the answer exactly. An inexact method might be to draw a tangent and do change in y over change in x. But a numerical method might be to take a point either side, for example, here and here. And if I've never heard of differentiation, but I do know how to substitute into an equation, I could put these two x values into the equation. I could connect those 2 points together, and the equation of this straight line that I've just made is going to be very close to the equation of the gradient of this straight line that I've just drawn will be very close to the gradient of the tangent at that point there. So that won't be exact, it will be close though, and that's an example of a numerical method where you pick a point either side and then you work out the gradient of that. That won't work out the exact answer there, but it works something useful out. And now the majority of numerical methods we will do will be concerned with iterations, and we're mainly concerned with locating roots. So here's a mystery function, or maybe later on I might even specify the exact function. And what I'm trying to do is figure out where does it cross the x-axis? What are the roots of this function? So far as we're concerned, the definition of root here is any value that makes the function 0. So if that number there is alpha, where it crosses the x-axis, then f of alpha would give you 0. And that would be the definition of a root. Alpha is a root if f of alpha equals 0. Okay. By convention, we typically use a or alpha for the root that we're trying to find. Suppose I don't know that point there, I'm trying to figure out what that is, I might call it alpha, and the whole game is, can you get close to alpha? Can you work out what alpha is? Now, the first and most important thing that we cover is a little exercise about sign changes. Now, suppose I told you that this was the number 1 and this was the number 2. So that's 1 there, that's 2 there. Think about what happens if I do f of 1. F of 1 goes across here, and you're going to get some positive number. Don't know what it is exactly, but it's a positive number. So f of 1 here is some positive number. But if I did f of 2, it's going to go down to here, and I get some negative number. It doesn't really matter what it is, but it's negative. That's a change of sign. Okay, when I put 1 into the function, I got one particular sign, and when I put 2 into the function, I got the other sign. It happened to be in the order positive first and negative second, but they could have been the other way around. The point is they're different signs. I've got a change of sign. A change of sign will typically imply that there is a root between them. Now, I need to be mega careful here because there's all sorts of caveats and exceptions and so on, which I'm going to run through in a moment. But that's pretty much the point of the whole first exercise that you will do, and pretty much for most of period 1 is an exercise where you're using the idea that a change of sign suggests that there is a root in the interval. So here, when I put 1 in, I got a certain sign out positive. When I put 2 in, I got a certain sign out negative. That suggests that there is a root somewhere between 1 and 2. Don't know what it is, right? It might be 1.5, it might be 1.7. In fact, it looks like a little bit less than 1.5 from my picture. So I don't know what it is, but it's somewhere between 1 and 2. Now, a change of sign here implied that there was a root in between. Now, we need to be a little bit careful because there's a few other sort of little caveats to this. If I had a graph that did something like this, okay, same thing would happen again, that f of 1 gives me this positive number here. So f of 1 is positive again, slightly more positive than last time. F of 2 will give me this negative number down here. So I've got a change of sign, but this time a change of sign did not imply a root. Actually, there are 3 roots in the interval. 1, 2, 3, all stuck in that between 1 and 2 there. So a change of sign doesn't necessarily imply 1 root, it actually implies an odd number of roots. Okay, there'll be an odd number of roots if you get a change of sign in that interval. I still need to be careful though. If I don't get a change of sign, that doesn't mean there's no roots. So for example, let's put 2 and 3 in this time. So if I put 2 in here, f of 2 comes out as some negative number down here. If I put f of 3 in, comes out as some negative number as well. So I don't have any sign change, but there are 2 roots in there. So it's the case that if there is a sign change, then there's at least 1 root. In fact, there'd be an odd number of roots. But if there's no sign change, there still might be some roots, and it'll be an even number of roots if there are. The last thing to be really careful about is if the function is actually discontinuous. So I'll actually give you an equation this time. So if I had something like 2x minus 2 all over x minus 2, so here I've drawn the graph with this equation. It has both a horizontal and a vertical asymptote, actually both at 2, and it crosses the x and the y-axis both at 1. But anyway, notice how a change of sign doesn't necessarily imply a root in that interval. If I put in, say, 1.5, so f of 1.5, I get some negative answer out. And if I put in 2.5, I get some positive answer out. But there was no root in there. That's because instead there was an asymptote. The whole function was discontinuous, we say. So if f of x is continuous, so that means it doesn't have any asymptotes. A continuous function can be drawn like without taking your pen off the page, but here I had to do that section and then that section separately with taking my pen off the page. So if f of x is continuous, and we have that f of a is a different sign to f of b, it doesn't have to be that that's negative and f of b is positive. It could be the other way around. So if f of a and f of b are different signs, then there is a root. So there is at least 1 root. In the interval AB.
Okay, so I don't know if it's one root or if it's 3 roots or 5 roots or 7 roots and so on, but there is at least one root, and it's an odd number of roots, assuming that it is a continuous function. It's not something that looks like this. Okay, now here I have an equation that I wish to solve. The way I'm going to do it is I will first of all turn this into a function which equals 0. So I'll take the 7 over to the other side, and then I can look for a sign change. I'll do that on my calculator. And so that is table mode is what I'm going to do. So I need to look for where it goes from negative to positive or from positive to negative. I need to look for a sign change. Now a sign change wouldn't have happened if it stayed equal to 7. If I didn't do this trick of putting the 7 on the other side, instead I would be looking for when do I go from one side of 7 to the other. So it's much easier to make the function, force it to equal 0, and then you can look for the sign change. Now on the class whiz, table mode is now mode number 9. So I'm going to type in 3 sine x plus 4x blah blah blah. You need to be in radians, by the way. So for this whole topic, later on we're going to differentiate some of the trig things. So you need to be in radians throughout, unless the question specifies otherwise. So I'm in radian mode at the moment. So 3 sine alpha close bracket is how you get x plus 4x e to the x. E to the x is above the natural log button. E to the x, and then take away 7. I don't need a second function. Let's go from 0 to 2, for example. I'm not sure how fine a steps I need. Let's look at 0.1s. Okay, so these are all negative to begin with early on, but they're getting higher, aren't they? And they're getting closer to 0. Oh, there we go. There's a sign change. That's my first sign change. So because putting in 0.6 gives me a negative answer and putting in 0.7 gives me a positive answer, I know there's a root to this equation, or a solution to this equation, somewhere between 0.6 and 0.7. I'm not sure exactly what it is, but it's somewhere between 0.6 and 0.7. Okay, so there's a sign change there. If you had to show that there is a sign, so if you had to show that there is a root between 0.6 and 0.7, you would just have to put those numbers down. You would say, well, you literally sub it in. So 3 lots of sine 0.6 plus 4 lots of 0.6 times e to the 0.6 takes 7 is minus 0.932. And you just comment that that's negative. You do the same for the 0.7 here. Hope you'll forgive the laziness here. And you would comment that this is 0.5711, etc., which is positive, and you say a change of sign implies at least one root. Okay, it's a little bit like when you do the factor theorem and you have to make a comment at the end. You can't just sort of miss it out completely. You have to make the comment, make it really obvious. Now, finally, suppose, like part B to a question, let's say, tells us that actually the correct answer to this is 0.66 to 2 decimal places. It's given, and we wish to prove that that is the correct answer to 2 decimal places. How would you prove that something is a root or a solution to a given amount of accuracy? This is where you need upper and lower bounds. So you would say that the lower bound for 0.66 is 0.655. The upper bound is 0.665. And then you do the same trick as you did here. So you'd put the lower bound in, and presumably in this case you're going to get a negative answer. You'd put the upper bound in, and you get a positive answer. And you say, oh, look, a change of sign in the interval implies a root between 0.655 and 0.665. But every single number on that interval would round to 0.66 to 2 decimal places. Okay, if you are a number that's somewhere between there and there, and I round you to 2 decimal places, you've got no choice but to go to that. Okay, so by definition, we did the upper and lower bounds for that number there. If it is possible to round you to something other than 0.66, then we didn't choose the correct upper and lower bounds to begin with. Okay, you're now in a position where you can have a go at the first exercise that I've scanned in. That's exercise 10A. Before you do, you might want to copy some of the pictures, some of the proper pictures from page 274 and 275. Also, the thing that I wrote up here is written in very, very exact language on page 274. So you might want to copy down like the exact statement for that. And I've got these sort of pictures up here, but they're sort of, well, they're nicer. There's sort of computer-generated graphs on page 174 of the scan. 274 of the scan that you might like to copy down. Then I was going to suggest that you try exercise 10A from the scan. Right, best of luck.